All right, so in this video, we're going to be talking about orthogonal and orthonormal bases. And basically, when you talk about these things, you're starting with a basis, and then you're adding additional properties to them. So let's recall, a basis is a set of vectors that are both independent and span the space in question. When you have an orthogonal basis, you are adding one additional property, and that is this is a set of vectors that are independent, span the space, and are orthogonal to each other. So mutually orthogonal. Now, an orthonormal basis takes this one step further. This is a set of vectors that are independent, span the space, are mutually orthogonal, and also are unit vectors. So the normal part of orthonormal is that normalization is that making these unit vectors. Now, in general, normalizing something can have different meanings in different contexts. We talk about normalizing in Markov chains so that the vectors all add to one. When we talk about normalizing eigenvalues, we just want to use small integer values when we can. But in this context, normalization does in fact mean making them unit vectors so that the length of of every vector is length 1. Now, matrices that have an orthonormal basis have special properties that we're not going to cover in this video, but instead we're going to talk about checking to see if our set of vectors does in fact form an orthogonal basis, and if they do, turning them into an orthonormal basis. So let's just start with the basic fact that the standard basis for every Rn space is already an orthonormal basis. Every vector is 1, 0, 0, 0, 0, etc., 0, 1, 0, 0, 0, and so on until you fill out the identity matrix. If you think about the columns of your identity matrix, they are all length 1. They're all perpendicular to each other. If you dot any vector together, you're going to get a 0 dot product. So the standard basis that we usually work in has all of these nice properties. It is not just a basis, but it is a really nice basis that has nice things going on with it. But let's think about a non-standard basis that might have these properties. So is the set of vectors an orthogonal basis? So let's look at an example in R3. So let's look at the following example. So 3 vectors. One, negative 1, 1. Oops, too long. 1, 2, 1. And negative 1, 0, 1. Now, so the question is, first of all, is this a basis? So if we were to put this into a matrix and row reduce it, we get the identity. So it is a basis. Row reducing produces the identity matrix. So it does span the space and the vectors are independent. Now to test for orthogonality, we're going to have to dot each of our vectors together to see if they are mutually independent. So we're going to are mutually orthogonal. So we're going to need V1 and V2. We're going to need V1 and V3, and we're also going to need V2 and V3. So let's think about V1 dot V2. So vector 1, vector 2, vector 3. So 1 times 1 plus -1 times 2 plus 1 times 1 is going to give me 1 minus 2 plus 1, which is 0. And if we do 1 and 3, so that'll be this one and that one, we're going to get 1 times -1 plus -1 times 0 plus 1 times 1, which is going to be -1 plus 0 plus 1, which is 0. And then if we do these two, then we're also going to get 1 times -1 plus 2 times 0 plus 1 times 1, which is going to give me -1 plus 0 plus 1, which is also 0. So these are mutually orthogonal, and so this is an orthogonal basis. If any of these dot products gives you something other than 0, it's not orthogonal. And therefore, it's not an orthogonal basis. Now, we're going to see in another video, the Gram-Schmidt process will allow us to take a set of vectors, maybe that is a basis, and turn it into an set of orthogonal vectors. Involves projecting onto a subspace and things like that, finding the orthogonal complement, essentially. But this Gram-Schmidt process will allow us, if in fact we had a basis, we wanted an orthogonal basis, we can make that conversion if we need to with that process. But for now, we're not going to worry about turning a basis into an orthogonal basis. We're just checking to see if it is orthogonal. Now, once it's orthogonal, we can turn it into an orthonormal basis. Make the basis orthonormal. So any process that involves making an orthonormal basis involves first starting with an orthogonal basis. We have that. So to make the basis orthonormal, we would divide every vector by its length. Now, the length of the first vector, if we use our magnitude formula, is the square root of 3. So our orthonormal basis will require this first vector to be divided everywhere by the square root of 3. Oops. There we go. Now the second vector, if I add these together, the squares together, 1 plus 4 plus 1, I get the square root of 6. So again, I have to divide everything by the square root of 6. Again, if you feel like rationalizing, that's perfectly fine with me. That doesn't always happen, but you can if you want to. And then it depends on your particular instructor, what their preferences are. And then this one has a length of radical 2 because there's only 2 components that are both 1. 0 divided by square root of 2 doesn't do anything. And so we end up with this is our orthonormal basis. To make an orthogonal basis orthonormal, divide every vector by its length. And again, the idea here is you don't need a magnitude for the whole thing. So there's not one magnitude that applies to everything. You're just going to take each column, you're going to turn it into an orthogonal. It's already orthogonal. You're going to turn it into a unit vector, and then that is your orthonormal basis. Now, it is very common to get crazy square roots when you try to do this. You do have to make your component selections very carefully if you would prefer to end up with like integer values. It is possible to do that sometimes to get nicer values that are, or at least like integer fractions, rational numbers, as opposed to square roots. But it is very uncommon, and especially if you're just making a problem up as an example, or if you're working with a lot of vector components, if you don't have a lot of zeros, you do end up with sometimes nasty looking square roots, which is why the identity matrix, the standard basis, is so useful, because it looks nice and it has all of these properties. And one of the reasons that it looks nice is because it is very simple, and it has all of these properties because it is simple. When you start complicating things, you end up with nasty. And so that's what we have. Something that looks somewhat unattractive, but it will have some nice properties of it that we may discuss in another video.